Okay, so off we go. Hope everybody had a good break. Welcome back and diving in. Real quick before we get into the math, you're going to notice that we have quite a few pages left to cover. And today is the last day we have to talk about Chapter 7. Because we do have all of Chapter 4 remaining that we'll be doing on Wednesday. And good news, Chapter 4 is very mechanical. It's very plug and chug, pretty much, and so that's going to be a reasonable thing. But still, getting through Chapter 7 is going to require a lot. So I am going to be kind of glossing over some of the stuff that's less critical, stuff that y'all are perfectly capable of reading on your own, etc., as I often have to do, tough choices and all that. And there are... there's at least one thing that I'm just going to cross out that you're not responsible for, and we'll get to that along the way. Okay, so here we go. We can do this. Okay, so reminder, last time we talked about Stokes' theorem. The very first thing we had to do is talk about boundary orientations. That's critical so that we can make the following observation. We need to be able to define boundary circulation, again, critically, specifically using the orientation we established about boundaries, and observe that it accumulates. It has this feature that the whole is the sum of the parts, and again, it's the usual picture, shared edge, opposite orientations, cancel. I've seen that several times previously. We've noticed that if you have an accumulating quantity, right, general statement that we made a while back, if you have an accumulating quantity, you can treat it like stuff. Stuff has an associated density. Circulation being the object in question, we're going to talk about circulation density. So how much of this accumulating quantity called circulation is there per piece of area that we're asking about circulating around? Right. And this is the formula for it. It's curl dot in, where in is the orientation unit normal. And that's about where we ended last time. And as usual, I'm not going to derive this formula. It's I'm going to say it's a lot of details. Very important, of course, but it's ultimately details. So the big punchline, and I think this is where we ended last time, we decided to entertain this stuff called circulation. We observed that it's an accumulating quantity. Accumulating quantities have the feature that stuff is stuff per unit size, namely density times size. ds, of course, represents the size of a little piece of a surface. It's our usual sort of, argument we've made several times in several contexts, but this is how you can argue when you have an accumulating quantity. And, well, boundary circulation is an accumulating quantity. And so we end up with a theorem. This stuff accumulates over the surface, and thus we end up with what at a glance appears to be a scalar surface integral. And then,
Is the n the unit normal here?
Yes, that's right.
But like previously in like other pages, we said that we could replace that with big N.
So big N comes from a parameterization, and here there is no
parameterization.
There's no parameterization here. Yeah, that's right. So there is another formula, but that would assume a parameterization that we don't have.
So if there was a parameterization, then we could use big N.
Not as an alternative, but there would be ways to rewrite this with big N.
With big N. Okay.
Yeah, that's just not what we're doing.
Here it is the unit normal.
It's the unit normal, the orientation unit normal.
Okay, thank you.
Yeah, sure. So we, argued that this was, accumulating over a surface, and that we're multiplying multiplying densities times areas, and areas are scalars. So we kind of expected this to turn out to be a scalar surface integral. But then you notice that is literally our ds, and so the more common way to write this, I'm going to say sort of unexpectedly, is that circulation, boundary circulation, is computed, weirdly, as a flux. Very unexpected, right? Not what we were thinking would probably happen. It's a flux of the curl field through the surface. Very weird. Okay, all right, so this is where we ended last time. Oh, yeah.
Where does the n go?
It's inside of this ds vector. So
yeah,
that's right.
That. Okay.
Yeah, no worries. Yeah, it is unfortunate that the ds scalar and the ds vector, they look a lot alike, and they look even more alike in the book where they just use bold. They don't even put the little thing over it. Yeah. Okay, so let's see an example of this in action, and let's see here. We're going to compute a line integral. It says, and various specifics are given. How are we going to compute this line integral? A quick reminder, don't forget we have various tools in the toolbox, right? And my gosh, this one comes with a parameterization. You're going to feel the urge to pull back through this given parameterization, and that would work, but it'd be pretty ugly, right? X, Y being these trig functions, you can see it's not a pretty calculation. You probably don't want to do that. We could consider the possibility of using the fundamental theorem of line integrals. It's worth entertaining. Doesn't work, as it turns out. In fact, when you try to find an anti-gradient, you would find that there is no anti-gradient to be found. So that's kind of a dead end. So we're going to use Stokes' theorem. Stokes' theorem says that if you want to compute a line integral, cool. Here's an alternative. You can compute that flux instead. The big catch, and this is a big one, real common landmine for students to step on. And we've seen an analogous story previously. It only works for boundaries. Only if you're talking about a line integral on a curve that is a boundary of a surface. Right? So, got to be careful about that. So that'll be the first question I'm going to ask coming down to this example. Is this curve, let's see here, parameterized like so? That's all we know about our curve C. Is that a boundary? Okay, well, we draw a picture of it. Think back to how we parameterize curves. I hope it's easy, not too hard to recognize. The unit circle is clearly related to this. This minus sign suggests a reflection. You kind of think through, what does that do? This is our final punchline curve. Is that a boundary? A lot of people will say no, it's going the wrong way. It's isn't it supposed to be counterclockwise or something like that? And no, that's two-dimensional thinking. That's, if we were talking about Green's theorem, that would be the case. This absolutely is a boundary. It's a boundary of this surface oriented downward, like so. And to confirm that the orientations work the way you're supposed to, the way that they're supposed to, remember, for surfaces in space, the rule is with the right hand, thumb in the direction of the normal vector, which is down in this case. Look at the fingers of your right hand. That defines a swirl, and the swirl here is, that wasn't what I meant to do. The swirl is kind of like that, and that side swipes up against the boundary curve exactly the way it's supposed to. So, all good. This is indeed a boundary. Everybody on board? Yep.
So this is what justifies that it's a boundary, or
exactly.
But also because it's downward, then would we have to put a negative in?
No, well, we'll get to the,
okay.
We'll get to that.
So it doesn't have to enclose anything.
Well, boundary of a surface is, there's some little annoying little issues. It's, the way I like to say it is, you could imagine an ant walking around on a surface, right? And if the ant's walking around, the ant is undisturbed by the fact that he's upside down because they don't weigh anything, right? They're practically massless, and they've got little sticky little feet. And so they don't notice anything until they get to an edge. And that's where they say, whoa, hey, what's going on here? The universe is, I've found the edge of the world, right? And where they start to freak out, that's what we call the boundary. So it's the curve edge of whatever surface. Okay, so we have a boundary, and because it's a boundary, boundary line integrals are flux of curl. So boundary line integral is a flux of curl. Notice that I've established that my curve is indeed, right, this curve is what we were given, is a boundary. So, you write down Stokes' theorem, and a couple of details that have to get worked out. You do have to compute that curl. Make sure you have that formula memorized. Make sure that you know how to do the plug and chug on that formula. How to compute a curl of a three-dimensional vector field. That's the result. We've already agreed that our normal vector is 0, 0, -1 because of our orientation discussion. And we've just turned a hard problem into a fairly easy problem. We have an integral of a constant over a garden variety surface, and easily concluded. Everybody okay? Yeah.
I don't understand how you got the normal.
So I have two options, right? So looking at this surface, and ignoring orientation, I can tell that this surface is fine. I just have to figure out which of the two orientations is correct. And you just kind of play the game. If I were to orient this way, and let's see, thumb, swirl, the swirl would kind of go around this way, which would have me going that way on the side swipe, and that's just wrong. So then you try the other, and for going the other direction, it works fine. Downward, thumb, swirl.
So x and y are zeros.
Correct.
And then the z would be a -1.
Yep.
Okay.
Yeah.
Thank you.
Okay. Alrighty. Okay, so several related ideas I want to talk about. Y'all will recall when we were talking about the fundamental theorem of line integrals, and that, by the way, that's this right here. There's fundamental. Oh yeah, I'm sorry.
I had a question above about why do we know that the radius is 1? I don't see that we were given that.
It's implicit in the fact that parameterizes the curve, and you can just infer it from.
Oh, just because it's sine and cosine.
Well, yeah, you can literally compute the distance to the origin. It's constant 1. So yeah. Okay. Alrighty. So so here's a take that I gave y'all when we were talking about the fundamental theorem of line integrals, and in particular, change is our stuff. That's our accumulating quantity. And I make the observation that stuff is stuff per unit size times size. Our size here is length. And so our stuff per unit size, our density, is gradient dot t. Right? But then, here's a different way to think about that, just a slightly more elegant. If you go ahead and combine TDS into dx vector, which is mathematically pretty natural, it's pretty geometrically natural, it's very satisfying in a lot of ways. If you do that, and then if you ask, how do I make sense out of this equation? I'm going to point out that you can think of dx as being, it's kind of telling you size, right? Its magnitude is the size, but it's also telling you a little bit more. It's telling you the orientation. It's telling you the t vector. It's implicit. It's wrapped up inside of the dx vector. That tells you the orientation. So I'm going to call this oriented size. And if you'll buy that, then gradient, being the thing that you multiply by oriented size to get stuff, I think oriented density is a reasonable thing to call that. So anyway, that's a take that we considered back in chapter 6. And by the way, neat punchline is that oriented density has actually a couple of different interpretations. The magnitude is telling you about the stuff in a pretty natural sense. It's telling you how steep the mountain is, right? But keep in mind, if you're on the side of the mountain, right, the mountain's going uphill that way, that steepness is in a certain direction. If I go that way, it's not going to seem as steep. It's literally not as steep, right? So yes, it's a steep mountain as per the magnitude of the gradient, but as I go in a specific direction. And the direction that I have to go to perceive that actual steepness is the other thing that the gradient tells us. So it tells you how steep is the mountain and in what direction is it that steep. Okay. All right. We can do the same thing with Stokes' theorem. Here's Stokes' theorem. And again, our standard take, looking at this being that, our standard take is that this is, of course, size. And that makes this, colors. That makes this our density. Density times size gives you stuff, as usual. Okay, but let's entertain what if we combine the scalar size and the orientation into a single vector differential. And by the way, that's exactly what we did up here. Exactly the same thing. Scalar size times orientation gave us our vector differential. We've talked about that analogy before. So if we do that, and then with that in mind, again, let's try to make sense out of this equation. I mean, with the understanding that this is now an oriented size, doesn't it stand to reason that this thing, curl, we should interpret as an oriented density? And of course, our quantity in question is still circulation, so thus the term oriented circulation density. And I know it's a mouthful, right? It's a lot, right? But the ideas all fit together. This is totally analogous to what we did back here, right? Just in a different context. So I think this is a really valuable point of view, thinking of curl as being oriented circulation density. And by the way, you get the analogous convenient interpretations. So the magnitude tells you how much the fluid is rotating, in the same sense that the magnitude of the gradient tells you how fast the function is changing. The magnitude of the curl tells you how much the fluid is rotating. But then again, just like with climbing the mountain, you got to go in the right direction. If you go the wrong way, you're not going to see that change that's suggested. So likewise, around what axis is this rotation happening? That's what the direction of the curl tells you. The direction of the curl tells you that, as the fluid is rotating, there's different ways that fluids can rotate, right? These are all different rotations that I'm doing with my hand here, right? Whatever the rotation is, U is telling you what is the axis that the fluid is rotating around, in effect. Okay, so here's the picture, sort of a generic picture of curl. So curl, this vector, tells you for your vector field F, whose curl we're talking about, how much of a rotation is happening, how fast is the fluid rotating, how powerful is this tornado, whatever, appropriate to the context, how much of a rotation there is, and then by virtue of the direction that it points, it's telling you what is the axis that rotation is happening around. So yes?
So if the curl vector is bigger, does that mean it's rotating faster?
Yep. Magnitude tells you in some sense how much rotation there is. And I'm leaving out a bunch of, if you want to talk about a physical interpretation of this, then you got to get real particular with units, and that's not what we're going to mess with in this class. But yes, bigger curl vector means, in some appropriate sense, more rotation. Yeah. All right. Now, just as a kind of a for example, and also I like to think of this as well as some satisfaction with this formula. My claim that circulation density comes from looking at a dot product with the orientation normal. That's kind of weird, a little unexpected that how much circulation you actually get depends on a dot product with the normal vector. A little surprising. So let's try to get some geometric satisfaction with that. And here's the big idea. Let's look at a couple of scenarios. Start with this first scenario here. And let's see here. Let me just get rid of that. If our curl is like so, well, our rotation is going to be kind of like that. That's how the fluid is rotating. And let's look at our little piece of surface that we have here. This little piece of surface, just looking at the picture, to what extent is that rotation flowing along that boundary? And I'm going to say quite a bit, right? I mean, look at the way this fluid is kind of rotating around. It's going the same direction that the boundary of that little piece of surface is. So I'm going to say geometrically we expect there to actually be a pretty significant, I put that in the wrong spot, pretty significant amount of circulation from what we see in the picture. Will this formula do that for us? Curl dot in, does that pick up on the fact that there's a lot of circulation? Well, yeah, totally. Right? The curl and the in, you look at that dot product, well, they're pointing kind of somewhat in the same direction. So the fact that the circulation is along the boundary geometrically aligns with the fact that the curl is in the direction of the normal vector. So hopefully a little bit of geometric satisfaction that dot product kind of makes sense. And then just for a sort of an example going the other way, let's consider the same fluid flow. Right? And now I ask, to what extent is that fluid, I don't know if I can do this with my hand, I don't know if I'm coordinated enough, but the fluid is kind of rotating this way, right? And then the boundary is kind of, I don't have the hand-eye coordination. Okay, the fluid's doing this, right? And the boundaries kind of go in, and they're just rotating around different directions. The flow of the fluid is not along this boundary curve. It's just not, you know? So, the circulation, you don't expect to get much circulation there. Does our curl dot normal vector detect that? Well, yeah, because this dot product would be small, if not zero. Because the curl is pointing this way, the normal vector is pointing that way. That dot product, not large. And geometric appeal, I claim this kind of always works. In some sense, how, let's see if I can do this with my hand, how the surface, let me come back up to here, to the top one, how the surface has its boundary aligned with the rotation of the fluid is kind of simultaneous with how the normal is in the direction of the curl. And as the surface moves in such a way as to sort of not hook up with the rotation of the fluid, notice the normal vector rotates away from the curl. So you kind of expect that this would generally be approximately right. Hopefully this is a good plausibility argument. This doesn't prove anything, right? I just want this to hopefully make this seem like a plausible claim. All right. Okay. Couple of quick observations about physical examples. Y'all will recall, of course, that if you have a vector field indicating the flow of a fluid, right, then curl is telling you what the implicit sort of related effective rotation of the fluid is. And I like this example because this contrasts with this false idea that curl is about flow lines, right? It's not about flow lines. It's got nothing to do with flow lines, right? It's about how leaves floating in that fluid will be rotating as a result. Right? It's about the rotation of the fluid, not the curvature of the flow lines. So pushing harder on this side, as this fluid does, we expect a counterclockwise rotation. And if you were to write down a formula for this vector field, and if you were to compute the curl, you would get a positive value, thus indicating counterclockwise rotation. Okay, same deal with three-dimensional curl. So here, I've got, let's say, air. And here, just to keep the picture simple, I am going with a really easy to draw rotation of a fluid. So here the fluid is very much just rotating around an axis like that. Right? Well, the curl of that vector field would tell you how the fluid is rotating as a result. And in the same way that I can think of this as a leaf and how the leaf rotates, right? Likewise here, I'm going to imagine a little balloon. I need it to be three-dimensional. I need it to be able to move around through space. So I'm going to say perfectly buoyant, right? Just that right amount of helium. 2 days after the birthday party, they kind of just float, right? So that's what we're talking about. And if the air has this vector field F, then the curl is going to tell you two things. It's going to tell you how fast will the balloons rotate and around what axis will that rotation be happening. Everybody buy it? And that's, keep in mind, we already know the curl is telling you how the fluid is rotating and around what axis the fluid is rotating. The balloon's going to do what the fluid tells it to do. All right, the next example is mostly a skip. This is a bunch of physics. It's not, if I remember correctly, not in the book. It's certainly not officially part of the course. You don't need to know this as far as Math219 is concerned. Now, that said, a lot of y'all are engineers. You are 100% going to need to know how magnetic fields work, right? I can't change that. So just as a real quickie, I will point out just a very broad strokes. When you have a flow of charged particles, we call this a current field. And we use very often the letter J to represent a current field, a flow of charged particles. The reality is that makes a magnetic field. Nobody knows why. This is empirical. Somebody noticed. Wow, check it out. Current makes a magnetic field. It just is, right? This is what we've observed. The magnetic field will do kind of like this. And we use the letter B very often to represent that magnetic field. The current field and the magnetic field will have a relationship in a way that's kind of analogous. Do you know how charge creates an electric field? Current creates a magnetic field. And there's two ways to write the relationship. And here's where we're getting into details that are we just don't have time for. I wish we did. But magnetic flux and total current relate to each other, and magnetic curl and the current field itself relate to each other. These are called Maxwell's equations. Right? This is what I call the fourth of Maxwell's equations. Again, two different forms. And again, what's the connection between them? Well, the big theorem in question. That was Gauss's divergence theorem when we were talking about electric fields and gravity and light bulbs and all of that kind of stuff. For this, it's Stokes's curl theorem. And notice, y'all will recognize this little square of equations, of course. We did something very like that when we were talking about electric fields and gravitational fields. It's morally equivalent argument adapted to the circumstance, and Stokes's theorem is the thing that makes it come together. Okay. All right. So that's just for your future use. Okay. filling in a quick blank. We've already done this. This is old news. This is straight out of chapter 6, literally copy-paste. Right? If you want to know if your vector field is a gradient, compute the curl, see if you get 0. If you do, yes, it is a gradient and path independent. If you don't, no, it is not a gradient, and no, it is not path independent. Right? It's a nice, simple test, what I call a local test, in the sense that curl is computed locally, and you're kind of getting a global conclusion about what it is or isn't based on something you compute locally. Okay, what made this argument work, you'll recall, is Green's theorem. Green's theorem is a connection between closed line integrals and double integrals. Green's theorem is what makes this argument work. It's doing the heavy lifting of this argument. Okay, now you'll also recall at that same time I cited an analogous result for 3 dimensions. Right? I claimed that to that same question, 3-dimensional curl works. And I didn't give you any justification. Because we didn't have the appropriate tool, and, well, we now do. Specifically, in 3 dimensions, the relationship between closed line integrals and now surface integrals is Stokes' curl theorem. So notice how it fits in exactly the same way. Right? In this and other ways, Stokes' theorem is kind of a 3-dimensional version of Green's theorem. Pretty meaningful way. Right? And this is just one of the several ways it does this. So again, we already knew this result. We don't need to repeat the result again. But if you have questions about path independence, or is there an anti-gradient? Am I going on a wild goose chase if I try to find an anti-gradient? You resolve that by computing the curl and seeing if you do or don't get 0. Okay. All righty. On to something new now. So y'all remember path independence. And just to set up an analogy, let me go through a quick reminder. Path independence entertains the situation where we have 2 curves, C1 and C2, that have the same boundaries. That is, they start at the same point and they end at the same point. Right? And with that understanding that these 2 curves start and end at the same 2 points, a vector field is path independent. What we mean by path independent is that the C1 line integral and the C2 line integral will always be the same, no matter what 2 curves, C1 and C2, that you pick, just so long as they share a common starting point and a common ending point. Everybody remember that idea of path independence? Okay. Now you'll also recall a different take on path independence is this idea of, well, you can kind of combine these 2 curves by going, around C1 and then C2. Notice, though, you have to go backwards along C2. This is a little weird thing about geometry that, C1 and C2 have the same orientation in the sense of how their shared boundary looks, but they kind of have opposite orientations in the sense of how they are a boundary of this region they enclose. So that's just a weirdness about geometry. That's intrinsic. That's not a notational mistake. That is intrinsic to geometry itself. So another way to phrase path independence, anyway, is that around a closed loop, the line integral has to be 0. So take your pick. The 2 different ways to say path independence. Okay. Turns out there is an analogous idea for surfaces. And the analogy is perfect. Totally awesome. Right? So if you understand path independence, and if you don't mind kind of using path independence then as kind of a guide, kind of kind of a list of suggestions for how to think in the higher dimensional case, you can totally understand surface independence. And here we go. We will entertain now two surfaces. Here's two surfaces that have the same boundary. Oh, wait a second. Oh, gosh. Curves have boundary points. Surfaces have boundary curves. Right? So where these two surfaces end, where the ant gets confused, either on the green surface or the blue surface, same curve. And in this scenario, we're going to define now something called surface independence. And surface independence just means that whenever the green and blue surfaces do as we've just described, that the green flux and the blue flux are always equal. Totally analogous. Again, I like to let the colors really kind of make it leap off the page how strong the analogy is. Right? So in the same way that path independence is about two path integrals always being the same under a certain condition about boundaries, surface independence is a statement about two surface integrals always being equal under certain conditions about boundaries. So, it's totally analogous idea. Again, there is an alternative point of view, which is you can think about the entire, sort of the whole surface together, which you notice, again, is the boundary of solid, right? And is that closed flux always equal to 0? So, totally analogous. Right? Here, these two curves, by having the same boundary points, bound an interior two-dimensional region. These two surfaces, by having the same boundary curve, enclose a three-dimensional region. Everybody happy with that? Okay. All right. So again, I just love how my God, it's exactly right. You look at the analogy; it's super strong. Please use this analogy, by the way. I'm a big believer. To the extent that you understand path independence, if there's anything you're confused about on the screen here about, wait a minute, what's the deal with, just look back up here and see what the analogous story is here. That'll be suggestive of how to think about the new idea here, yeah.
So if it is surface independent, then the integral is just 0?
The closed, fluxes through a closed surface S must be 0. That's right. In the same sense that if you have a path-independent vector field, line integrals around closed curves have to be 0.
Okay.
Right. So, and we saw some examples of it. I think the example we did with, I made a reference to, old people claiming that it was uphill both ways. It adds up to 0. Right, closed line. I mean, if you're talking about how you moved around on the, how your altitude changed as you walked to and from school, that adds up to 0 because it's closed curve and gradients are path independent. Yeah.
But that's if we're considering the entire boundary.
Exactly.
So is there a link between the first line,
between this line and this line?
Yeah.
Oh yeah, absolutely. So these, if you look at the green and the blue integral up here, right? Keep in mind the orange integral is just a combination of the green integral and the blue integral, and if these are the same, then their difference is 0.
Okay.
And so likewise here, if these green and blue fluxes are the same, then their difference is 0.
Okay. Thank you.
And again, this minus sign is intrinsic to geometry. There's no way around it. This is not a unfortunate notational choice. This is unavoidable. There is such a minus. The minus sign is there whether we like it or not.
Thank you.
Yeah. Okay. All right. Now, when we were talking about path independence, at some point, I noted that there are some easily noted path-independent vector fields. Gradients. Gradients always do this. And a great way to see that gradients always do this is to use the fundamental theorem of line integrals. Just write it down and it totally works. Well, there is a automatic freebie surface-independent vector field, and that is curls. Any vector field that is a curl of something else is surface-independent. And how are we going to see that? Well, it turns out the fundamental theorem of line integral is not the right tool, but Stokes' theorem is. Stokes' theorem says that, all right, well, if you've got, one surface and another surface that have a common shared boundary curve, right? Well, the fact that they have a common shared boundary curve, if I write down Stokes' theorem in each of these cases, Stokes' theorem tells me each one of these fluxes is a line integral around the exact same boundary. And so you're going to get the same answer for both the green and the blue, and thus surface independence. So again, lovely little argument. It's a good one to think through and digest. And so every curl is surface independent. Now, harder to prove, still true, and something that you should know for our purposes here. Not only is every curl surface independent, every surface independent field is also a curl. Let's not worry about regularity issues. That's not what this course is about. So as far as we're concerned, as far as nice, appropriately regular vector fields are concerned, vector fields that are surface independent are the exact same vector fields as vector fields that are curls of something else. Okay. All right. Now y'all will recognize this little layout. We have yet another example where we can apply this layout. We just got through discussing how these are all simultaneous. A vector field that's surface independent means that closed fluxes are zero, which means that the vector field is a curl of something. Okay. And I hope it's not a hard pitch that these two equations are the same. If all triple integrals of some function are zero, what function could this possibly be? All triple integrals of it are zero. All triple integrals, no matter what the region is? Come on, there's a function whose all of whose triple integrals are always zero. It's got to be zero. What other function could do that? Continuous function, of course. So we've talked about the green. I think the blue is quite closely connected to an argument we made previously. How do we connect these two connections? And Gauss's theorem. Gauss's theorem tells us that closed fluxes are triple integral of divergence. So therefore, we have this nice little connection here, and more importantly, here. If you find yourself looking at a vector field and you would like to know if that vector field is surface independent, how are you going to decide if a vector field is surface independent? Take the divergence. See if you get zero. If you take the divergence and get zero, go around the circle whichever way you like, but if the divergence is zero, that vector field is surface independent, and that is a very powerful computational tool. And I'm going to show you an example where we're going to use this pretty big time. And by the way, for reasons I don't really understand, surface independence, not only is it underrepresented in our textbook, it is underrepresented in most multivariable calculus textbooks. Path independence is all over the place. Surface independence, barely mentioned, if at all. Super weird. Okay, let's do the example. Notice we want to compute a flux. We got a surface given. We got a vector field given. Let's consider our options. You could plug and chug. You parameterize that surface, graph parameterization. You got a vector field, you plug that in. It's going to be massive polynomial, lots of polynomial stuff. You'd end up with an integral on an ellipse. It's doable, right? You could totally do that. But here's a better way to do it. In this case, anyway. Let's entertain this vector field, and let's see what can we conclude about this vector field. Keeping in mind this result up here. If you would like to know whether your vector field is surface independent, compute the divergence, see if you get 0. And you take the divergence, you get 0. Yes, you've got a surface independent vector field. And as this says, if you want to compute this integral, okay, throw it away. Compute a different integral instead, just making sure that your two surfaces have the same boundary. So, all right, so let's do it. Let's see. Okay, well, I'll leave that there. So here's our vector field. Compute the divergence. Easy partials, right? The x partial of this is obviously 0. The y partial of this is obviously 0. The z partial of this is obviously 0. And our divergence is 0. Our vector field is surface independent. We've got options. I can take this surface. I can pick any other surface that I want. Right? Think strategically. Channel your inner laziness. Find the easiest possible surface that you can use. And yeah, go ahead. The vector field is surface independent. It's all good. So, for example, let's see here. Our surface is this right here. Now, before I go on, I just want to emphasize very common landmine to step on. Super common mistake. A lot of students do this. It does not include this down here. You got to be really careful about how you read this stuff. Right? So a lot of students will see, okay, paraboloid, plane, and then they kind of see like a little solid lump and be like, okay, the surface must be the boundary of that lump. Not at all what this says. It's just not what this says. This says S is part of the paraboloid, right? Everything here, all of this is just a clarification of which part of the paraboloid. Is everybody okay with that? Everybody clear? It does not include this bottom face. Okay. All right. Yeah.
But if you take z equals to 0, then you're technically closing it, so it will include it. Like if
this were phrased in a very different way, then there is a different phrasing of a totally different question that would include the bottom. But my point here is that this phrasing doesn't. Yeah. No, there is, right? Absolutely, but it's just not what we're doing here. Yes.
So why doesn't it include the bottom if z is greater than or equal to 0?
Yeah. Okay. So S is part of the paraboloid, right? Which part is a little side deal that tells us which part of the paraboloid, but specifically the paraboloid. And only the paraboloid is what our surface is. You see what I'm saying?
It touches z equals 0 only on the edge.
So, z greater than or equal to 0 is basically saying, I just want the part that's above the xy plane. That's a clarification of which part of the paraboloid we want. Is that satisfying?
Yes.
Okay.
Thank you.
Yeah, no worries. Okay. All right. Oh my gosh, by the way, I see this kind of mistake so often, and it's a huge mistake, and it will give you dramatically wrong answers, and it just gets you going in the wrong direction very early on. It's another one of these situations where students lose a lot of points because nothing they've written down is relevant to the question that was asked. And so anyway, please be very, very careful to interpret appropriately. And with that noted, let's see here. We've got a surface-independent field. That surface has a boundary which is this curve. That's a geometric appeal. That curve is our boundary, right? It's like a wine glass turned upside down, right? The boundary is the lip of the glass. Wait a second, we got to think about orientations. Our surface is oriented downward, in other words, like that, and so you got to think about the swirls and everything. Our boundary is going to be oriented this way. So my charge now, when I got a surface-independent vector field, I get to pick any surface I want. Any surface I want, as long as it's got this same boundary. Let's start thinking about, by the way, let's get rid of the blue thing. We don't need the blue anymore. We're jettisoning that surface. We just need to find any other surface that has this purple curve as its boundary, orientation included. And I think it's a pretty easy pitch that this surface here in green has the right edge. It's got the ant gets confused at the exact same points. Right? And think about the orientation, and let me see if I can zoom. There we go. If you, let's get it wrong first, just for fun. If you were to orient it the wrong way, thumb, fingers, swirl, the swirl would be like this, and that swirl is just going the wrong way. And so we try again. Oh gosh, if I can, we try again. Orient like this, thumb, fingers, swirl. The swirl goes around like this, and that is the correct orientation. So there's our normal vector. And it's basically all over but the shouting now. This new surface, this green surface, is so much easier to work with. Super easy to work with. For one thing, look how easy the normal vector is. That new green surface, its normal vector is mostly zeros. Awesome, right? Also, for this entire green surface, z is 0. So working on this integral, not the original integral, but on our new integral, you just get to say, hey, you know what? Z equals 0. And life is good. And what you end up with, and y'all can check the details, you end up with this double integral, which is 0 by symmetry. And we're done, and we didn't have to do anything dirty. Nothing ugly. Powerful arguments. Okay. All right. So just real quick. Oh gosh, I know I'm over. Sorry. I want to remind y'all about these diagrams. More to the point, we have the other version of the diagram here. We've actually now discussed all of the ideas on this page. I've already walked you through. You might want to re-listen to that stuff from chapter 6. Where I was talking about how the patterns hold extremely strongly. Please take a moment to watch that again or remind yourself of those patterns and notice how they fit together in powerful ways. And then last thing, there are 6 examples that follow. These are supplemental. These are, there's nothing in any of these examples that we haven't already covered. But I like having additional examples at the end because there's no context clues. Like if I give you an integral to compute in the section on Green's theorem, you kind of know Green's theorem is going to be the way to do it, right? These are presented, no context given. And so anyway, I'm going to send y'all some videos. I say send. I'm going to post on the YouTube channel some videos that I recorded a couple years ago going through all these examples in detail. Hope you'll watch. See y'all later. Have a good one. Don't forget about attendance.